Jnanam paramam dheyam. Knowledge is supreme.
What was property 3? That said every element has got a representation and 0 has unique representation. The unique representation property is an important one, which will let us signal it out. Okay, right? It says a set of vectors in Rn are called linearly independent. So that property that 0 has unique representation, meaning what? If sigma alpha I vi is 0, then each alpha I must be 0. So that property is called the linear independence, right, of the vectors v1, v2, vk. So a set of vectors is called linearly independent if a linear combination of them equal to 0 implies all the scalars are equal to 0, right. So and if they are not, what is the opposite of it? That means there is a linear combination which is 0, but not all the scalars are 0. That is called that property is called, that set is linearly dependent, right. So opposite of independent, we will say it is dependent. Independent means 0 has unique representation, and dependent will mean that 0 does not have. That means sigma alpha I vi equal to 0 for not all alpha I equal to 0. Such a relation should be possible. So let us look at some examples. Can I say the vectors v1, v2, v3 in R3, right? There are 3 components. The vectors are v1, which is 1 0 0, v2 is 1 1 0, and v3 is 1 1 1. I want to check whether they are linearly independent or not. So how will you check something is linearly independent? Uniqueness of representation for 0. So take a linear combination which is equal to 0. Does it imply that all the coefficients involved are 0 or not? So let us check that. So let alpha v1 plus beta v2 plus gamma v3 be equal to 0, right. So what does that mean? Alpha times what is 1 0 0 plus beta times 1 1 0 plus gamma times the third vector 1 1 1 is equal to 0. Let us simplify. What is it meaning? It means alpha plus beta plus gamma, that is the first element, right. What is the second? That is beta plus gamma, and that is the third one, that is gamma, right, should be equal to 0, right. I have just added those vectors, but that means what? Alpha plus beta plus gamma, first the first equation, that should be 0, second beta plus gamma should be equal to 0, and third says gamma should be 0, right. So these 3 equations must be satisfied, and now just gamma is equal to 0. If I put it in the backward here, gamma is 0, that means implies beta is equal to 0. Now alpha and beta both are 0, put the values here, that says beta and gamma are 0, that is implies alpha is also equal to 0, right. So that says that these 3 vectors in R3 are linearly independent. So okay, right. So implies v1, v2, v3 are linearly independent, right. So that is a proof that I just now gave, that the linear combination must be equal to 0. Let us look at another example. Let us look at S is a set of 3 vectors, right. First vector is 2 minus 4, second is 1 9, and third is 3 5, right. This is a subset of R2. Each vector has got 2 components, and we have got 3 vectors. We want to know whether they are independent or not. Here it is quite easy to see that you can represent a linear combination of it equal to 0. So, how will you make the first one 0? So, first component, for example 2, right, 2 plus 1 minus 3, that will give you first 0, right. So, it says a possibility, right. So, let us, if you look at C1 times the first vector plus C2 times the second plus C3 times the third one, where C1 is equal to C2 and last one is minus 1, this linear combination is equal to 0 and the coefficients involved not all are 0, in fact none of them is 0, right. So, I have got a linear combination of the 3 vectors equal to 0. So, 0 does not have a unique representation in terms of these vectors 3. So, what does it mean? The meaning is that these 3 vectors are not linearly independent, right, they are linearly dependent vectors. This phenomena will observe, this is going to happen very often, in the sense that, see, these are 3 vectors of 2 component each. So, whenever you will have a collection of vectors where the number of components is less than, right, number of components is less than the number of vectors, they are going to be linearly dependent vectors always. Can you see the reason why it should be? Let us just write and see whether why that should be true. If alpha 1 V 1 plus alpha 2 V 2 plus alpha k V k is equal to 0, right, that means alpha 1 of A 1 1 A 1 n, right, or probably I should write other way around. V 1, it has got n components, right. Okay, let us write what is V 1. This writing is a, so first component of V 1, right. So, we want to write as the first row, okay, A 1 1, second row, so A 2 1, okay, and we have got n, so A n 1, is it okay, right. So, and V k will be A 1 k A n k, right. So, then this equation is just writing it as A 1 1 A n 1 A 1 k A n k applied to alpha 1 alpha k, right, is equal to 0. So, this equation is same as saying this equation, right. So, now how many equations are here? N equations in k variables. So, this is equivalent to, so alpha 1 V 1 plus alpha k V k equal to 0 is equivalent to giving a system of equations, right. So, we have got n equations in k variables. What are the variables? K variables alpha 1 up to alpha k are the variables, right. So, n equations, and when does a system of equations has a non-trivial solution? Is a homogeneous system, it always has a solution 0. When does it have a non-trivial solution? When the rank should be less than the number of, right, rank should be less, not the full rank, right. Here what is the rank possible for this system? The rank, it should be less than the minimum of n and k, it should be minimum of n and k, right, minimum of number of rows and number of columns. So, if number of variables, what is the number of variables? If k is strictly bigger than n, so this is the assumption we are making, if the number of variables, that is k, is more than n, then what will happen? Then the rank will be always less than is the minimum. So, what is the minimum of k and n? That is n. Rank will be less than or equal to n, right, which will be less than of course k. There are k variables, right. How many variables are there? K, alpha 1 to alpha k, and the rank is strictly less than k. So, system of equations is consistent with actually infinite number of solutions, right, when the rank is strictly less than. So, implies system has infinite solutions. Is it okay? Going back to system of linear equations, if the rank is strictly less than the number of variables, then how many variables get arbitrary values? Number of variables minus the rank, right. So, k minus the rank, number of variables will get, and k is strictly bigger. So, there will be at least one variable getting arbitrary values, right, could be more. So, that means there are infinite number of solutions possible. That means what? That means in this linear combination I can have infinite many solutions of alpha 1, alpha 2, alpha k, such that this is equal to 0, right. That means if I have got more number of vectors than the number of components, then that set is always linearly dependent, and that is what is happening in this case. I have got components 2, right, number of vectors is 3. So, this has to be linearly dependent, and we verified that actually there is a possibility here, right, but that is a general solution, and that is quite useful writing later on, that if you are given a set of vectors, right, first see the components and the number of vectors. It may be obviously linearly dependent if possible, right, the number of vectors is more than the number of components. So, let us I have just recaptured all this in this slide. B is linearly independent set, right, and this 2 is a redundant thing, actually this should not be there, right. So, B is linearly independent and the span is V, right. So, itemized we should remove. B is maximum linearly independent or as a minimal this should be a minimal set, right, minimal minimal not again independent. I think this is a all is wrongly typed thing. Is it clear? Anyway, wrong thing also helps you to understand what should be the right thing. So, the first is B is linearly independent and spans V, that is 1. Second, maximum linearly independent, and the third is a minimal set which generates. You do not have to put linear independent then. Okay. So, now let us we said number of a vector space can have more than one basis, we saw that. So, let us construct one more example to say that a vector space. Okay. So, let us look at so consider V equal to R2 itself. I think we have done for a lot of examples for R2, but it is good. Let us V equal to R2. Let us look at the set B1, which is our 1 0 and 0 1, right. So, what is why it is a basis? B1 is a basis. Why it is a basis? One, I should be able to check either by either of the definitions, right. So, let us check that B1 is linearly independent, is a linearly independent set. So, how do I check it? Check alpha times 1 0 plus beta times 0 1, if it is equal to 0 should imply alpha equal to beta equal to 0, right. So, what is this equation? That is same as alpha plus beta comma, no sorry, this is same as saying alpha comma beta equal to 0, right, alpha 0 plus 0 beta. So, that is alpha comma beta, and that implies alpha equal to beta equal to 0. So, linear independent, right. I should check either it is maximal, right, or everything generates, either of it is okay. So, now let us look at for every x comma y belonging to R2, I can write x comma y is equal to x times 1 0 plus y times 0 1, right. So, what does this imply? That means x y belong to any vector in R2 belongs to linear span of B1, right. Is it okay? It belongs to linear span of B1, because this is one vector 1 0, there is other vector. So, linear span of B1 is the whole space and it is independent. So, it generates L of B is equal to S and linear independence, that implies it is a basis. So, implies it is a basis. Let us construct some other example, another basis. So, let us look at B2, say let me keep 1 0 and let us take 1 1, right, that is another set in R2. Claim B2 is a basis. I can use any one of those three. So, let us check independence first of all, if we can check independence, right. So, alpha of 1 0 plus beta of 1 1 equal to 0. What does that imply? A linear combination equal to 0. What does it imply? It implies alpha comma is alpha plus beta comma alpha comma beta is equal to 0, right. So, that means alpha plus beta is equal to 0 and beta equal to 0. So, that implies alpha equal to beta equal to 0, right. So, the set B2 is linearly independent. Next, what should I check? If I want to show it is a basis, either I should show it is a maximal or it generates, either of it. So, let x y belong to R2. Can I find alpha beta such that x y is equal to alpha times 1 0 plus beta times 1 1. So, that is a question, right. If I can find, that means this will have a x y will be a linear combination of these two. So, what does it mean? That is alpha plus beta comma beta. So, that means what? So, this is the same as saying that alpha plus beta is equal to x and beta is equal to y, right. What is given to you? X and y are given, that is a vector given to me. I want to find alpha beta. So, what this implies that this beta is equal to y. So, what is x? So, that is x is equal to alpha plus y. I put back the equation here. So, what is x? Oh, right, beta is, I want to find alpha, right. So, alpha is equal to x minus beta, and that is what I am trying to look for? Alpha, we want to find alpha beta such that this is equal to so. So, alpha plus beta is equal to x, beta is equal to y. So, okay. So, x minus y, right. X and y are given to us, we want to find alpha beta. So, I put in this back equation, okay. Beta is y, so goes that side. So, I have found. So, for this choice, so hence what does it imply? Hence the linear span of B1 or B2 we called it is also equal to R2, right. So, we have verified both the things, linear span is equal to R2 and it is linearly independent. So, hence the set 1 0 1 1 is also a basis, of R2, right. So, given a vector space, there could be more than one basis of that vector space possible. So, that is what the remark says, a vector space can have more than one basis. However, a theorem in our subject says that any two bases of the vector space will have same number of elements. The number of elements in two different bases has to be same, it cannot be, right. One cannot have, say in R2 we said we had B1 and B2, both had two vectors, right. One of them alone will not be able to generate. You want to see why? Let us see B1. What was B1? 1 0 and 0 1, right. If I remove one of them, what do I get? Only 1 0, and what will the generate? What will it generate? Linear combination x comma 0. So, that is only x axis, right. Other one alone will give me only y axis. So, I cannot make it smaller anyway. If I make it bigger, if I add a third element to it, then it becomes linearly dependent. Independence is gone then. Just now we saw 3 vectors of 2 component each will be dependent. So, it cannot be that, right. Similarly, in the other one, in the other example, if I look at this, if I cannot remove either of it. If I remove 1 1, I get only x axis. If I remove 1 0, what do I get? X is equal to y, right, the line y equal to x. So, that is not the whole of plane, right. If I add one more, then does not remain independent again, the problem, right. So, in R2, the number of elements in a basis, how different bases are possible, number of elements is same, that is 2. So, you will say the dimension of R2 as a vector space is 2. So, we can define it for anything now, the number of elements in any vector space, right. V is a subset of Rn, which is a vector space. So, in any vector space is the unique number, that is the number of elements in the basis, and that is called the dimension of the vector space, right. So, one, we showed every vector space has a basis, right, and secondly, this theorem we are not proving that any two elements in the the number of elements in a basis is unique. That means, any two bases will have the same number of elements. We are assuming that as a consequence of it, every vector space you can associate a unique number, the number of elements in any basis of that which exists is called the dimension of it. In some sense, that is a size, you can think of it as a size of, right. So, let us look at some more examples. So, let us look at this, consider the system x plus y minus z equal to 0. So, x plus y minus z equal to 0. So, we want to look at the solution space of this system. What is the solution space of this system? What does solution space mean? It is a set S, right, of all x, y and z. If I write it as elements of R3, there are 3 variables such that x plus y minus z is equal to 0, right. As a set I can write this. So, what is the order of the system? What is the order? 3 variables, 1 equation. So, 1 cross 3, right, is 1 cross 3. Okay. So, what is going to be the rank of, to find all solutions is a homogeneous system. So, it is a homogeneous system, right. So, what is the rank of this? rank of the system, yes, rank is equal to how many pivots are there? 1, which is less than 3, the number of variables n. So, that is R and that is equal to n. So, how many solutions are possible? Yes, consistent infinite solutions, right, and we gave a method of saying how do you find the infinite solutions. Where is the pivotal column? Pivotal variable is x, right, the pivot comes in the very first stage x. So, the value of x should be found in terms of y and z. So, we find value of x in terms of values of y and z. So, let us do that. So, let us put arbitrary values. So, let y be equal to 1, z be equal to 0. Then what is x is equal to 1 minus 1. So, what is y? So, x is equal to minus y plus z. So, what is that? Minus 1 plus 0, that is minus 1. So, that is for this thing. So, let us take another value. Let us take y equal to 0 and z is equal to 1. Then what is x is equal to? So, that is minus y plus z. So, that is equal to 0 plus 1, that is equal to 1. So, I got two solutions. So, we have V1. So, what is V1? So, V1 is equal to we got y equal to 0, x is equal to minus 1. So, minus 1, 1 and 0, that is one solution. Second solution is V2, we got x is equal to 1, y equal to 0, z is equal to 1. I got two solutions, right. So, let us form the set, let B be the set V1 and V2. Okay. So, if I can show that this set B, right, this is a subset of S, that vector space S, all solutions. If I can show that this is generating everything and it is linearly independent, then this will form a basis for the solution space, right. This will form a solution for the this will form a basis for the solution space. So, how do I check the independence? So, let us check independence. So, claim B is linearly independent. So, what does that mean? Alpha V1 plus beta V2 equal to 0 should imply alpha equal to beta equal to 0, right. So, what is it? Alpha times minus 1 1 0 plus beta times 1 0 1. So, that is equal to 0, that implies minus alpha 0 plus beta 0 beta, that is equal to 0. So, that implies minus alpha plus beta, the second one is alpha and third is beta equal to 0, right. So, that clearly implies that alpha equal to beta equal to 0. So, linear independence. Okay. Does it generate everything? So, does it, does that means can I say L linear span of B is equal to S, all solutions are linear combinations of this, right. So, that is we have to check. So, let us check that. You can write a general solution as here called V1 and V2. So, what does the general solution look like? Okay, let us say what is the general solution. So, if a vector v belongs to S implies what was S equal to, that is x, y and z, such that x plus x minus y, x plus y, what was it, x plus y minus z equal to 0. That means v is equal to, so what is the solution? What is x is equal to? I can compute x in terms of y and z. So, what is x from here? X is equal to minus y plus z, y and z. Is it okay? V should be of this form, where x and y are some constants, I do not know, for some x and y, right. So, that means, so let us write this. So, that is equal to, can I write this in terms of V 1 and V 2? I want to write as B V 1 plus alpha of V 2, where, see, that is what I have written there, where what is beta? What is alpha and beta? You can put arbitrary, it does not matter. You can put alpha and beta are arbitrary. If you want, if you know V, you can get alpha and beta, you can compute that from the system of equations, right. If V is known to you, then you can write down the system of equation and get the solution in terms of alpha and beta, in terms of that components of V. But that itself says that V should be equal to this, right, where alpha and beta are. That means what? Every solution is a linear combination of V 1 and, that says it is a linear combination of V 1 and V 2. So, this is linearly independent, that set B, right. Those two elements are linearly independent and span everything. Every element is a linear combination. So, implies B is a basis of the solution of the set S, which is all x, y and z, such that x plus z equal to 0, right. So, what we have done is, given a system of equations which had infinite number of solutions, there were two free variables, we put them special values and got a basis for the solution space. That means, the solution space for this particular homogeneous system is written as a linear combination of only two vectors, right. So, that is the advantage of basis. So, we will continue this next lecture.